That's what's going to happen today.
So
let's go for it.
I unfollowed him. No, I unfollowed him, and then he went private. So I messed he still follows me. Dude, there were so many subtweets afterwards. Oh my god, it was so funny. Yeah, and then Anthony insulted me too. No, there's a bunch of band kids talking to me, but they weren't able to do anything because they don't know how to mess with Gabe. Like I do. They're just like, oh, your water polo sucks. It's like, yeah, we only suck. We all mess around in practice, okay? You know that. Okay, when we swim, we can't mess around, okay? Like, there's not much we can do right now. But everyone, even when we swim, people are slacking. You see, look at them, they're not trying hard enough. And then look, he's out halfway through the period.
Looking at example 4, I just want to make you aware of something. Since the derivative of the velocity is equal to the acceleration, if someone gives you a velocity versus time graph, it's very easy to get the acceleration. All you have to do is look at the slope of the velocity versus time graph. So, and those of you who haven't trained physics may recognize this. So, like, look at this graph here, from 0 to 1. I say here, find the acceleration from 0 to 1. Well, you tell me, what's the acceleration of this particle from 0 to 1, if that's a velocity versus time graph?
10 meters per second.
You guys getting 10 meters per second? Because that's the slope of the graph. Remember, the units of slope are going to be rise over run. And so the units of the rise are meters per second. The units of the run are seconds. I've neglected to put it down. I feel really bad about that. But because I don't think I expected to be showing my notes on the board. But the point is, the units of slope for a velocity versus time graph is meters per second, which is the units of acceleration. And so, yeah, the acceleration from 0 to 1 seconds is 10 meters per second. You guys tell me, what's the acceleration from 1 to 2 seconds?
0.
0. Good, because there's no rise here. That is, you're going at a constant velocity. There is no change in your acceleration. Acceleration is the change in your velocity. With respect to time, well, there is no change in velocity, so there's no acceleration. How about from 2 to 3? What's my acceleration now?
Negative 10 meters per second.
You guys getting negative 10 meters per second?
Yes.
Good. And how about from 3 to 4?
0 meters per second.
Good. And finally, I'm going to let you guys do this. How about from 4 to 5? What's my slope now?
Negative 20 meters per second
If
squared.
you guys are getting negative 20 meters per second, you win. The rise is negative 20. The rise is negative 20 meters per second. The run is 1 second, 20 meters per second. And finally, from 5 to 6, it's 0. Good. Let me ask you this. When is the speed maximum? At what times?
1 to 2 seconds.
When is the speed maximum?
Oh, 4 to 5.
Good. Or I mean, no, not 4 to 5.
Oh, 1 to 2. 1 to 2.
No, not 1 to 2. Keep going.
Oh, 5.
What's that? 5? Is that the only time when the speed is maximum?
Oh, and 5 to 6.
Thank you very much, Abigail. Why do you say 5 to 6?
Because speed has no positive or negative direction. So
Beautiful.
take the absolute value of the velocity.
Good. You guys okay with that? The fact that it's negative is irrelevant. Speed is just magnitude. You're going fastest from 5 to 6. You're going 20 meters per second. At no other time in this trip are you going as fast as 20 meters per second, except right there from 5 to 6. So that's it. That's the speed is maximum from 5 to 6. Okay. Tell me, for what times is the person going forward?
1 to
0 to 1.
0 to 2.
Good. He's going forward from 0 to 1. Any other times?
1 to 2.
Is he going forward from 1 to 2?
Oh, yes.
Sure. How fast is he going?
10 meters per second.
10 meters per second forward, right? The fact that his velocity isn't changing doesn't affect the fact that he's going forward, you know? You guys okay with that?
Yeah.
He's going forward from 1 to 2. Is he going forward from 2 to 3?
Yeah.
Why? Why would you say he's going forward from 2 to 3? Yeah, Lauren.
He's just decreasing his velocity, but he hasn't turned around.
Thank you. He's decreasing his velocity, but he hasn't turned around. I just repeated what Lauren said verbatim. Yeah, see, his velocity is still positive, so he's still going forward. Sure, he's slowing down, but he's still going forward. Tell me, is there some time here where the guy is totally stopped? 3 to 4. Is he stopped from 5 to 6? The slope of that graph is 0. Does that mean he's stopped from 5 to 6?
No.
Heck no. No, he's only stopped when he hits the x-axis. There's one other time when he stopped besides 3 to 4. When else?
0.
Yeah, it's 0. He starts from rest. Good. And finally, when is he going backward? From what times? During what times is he going backwards? Hopefully he's saying 4 to 6, right? Why is he going backwards from 4 to 6?
Because his velocity is negative.
Good, velocity is negative. We're going to be doing this sort of thing a million more times. This was the first time you calculus kids had to deal with this issue, and you did fine. So that's it. That's example 4. That's all I need to show you right now. It is now time to do derivative of the trig functions. Do you remember when I was showing you the derivative by using calculators, and I showed you the graph of sine of x, and then we graphed the derivative of the sine of x? Do you remember which trigonometric function we ended up graphing? Cosine. So you guys remember that the derivative of the sine of x is the cosine of x. I would now like to show you a proof of that using the limit definition of the derivative. And please don't copy this down. I'm just going to show it on the board, and we'll look at it and enjoy it. Or show it on the screen, rather. But I certainly don't want you to write this down. Please, 1 second. All right. That way I don't have to write it on the board. Can you guys see that okay?
Yes. Can I take a picture of that?
Yeah, sure. You can take a picture or video of anything happening in this class. I have complete transparency in this class. Nothing happens here that I don't mind if your parents know about it.
No censorship. Like.
Okay, great. What's the derivative of the sine of x? Well, we found that it was a cosine of x by graphing. Now I'm going to prove it using the limit definition of the derivative. Here we go. The derivative of the sine of x is the limit as h approaches 0 of sine of x plus h minus sine of x over h. You guys okay with that? And then I'm going to do something really tricky here. I'm going to say, okay, let's do the alpha plus beta. Do you remember that sine of alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha? Does that ring a bell from last year?
Which one?
It's the sum angle identity. Sine of alpha plus beta. Sine of alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha. Okay. Hopefully no one actually remembers that, because I don't. I couldn't tell you them right now. I mean, why would I waste precious brain? You know.
I remember doing it though.
Yeah. I mean, I can look it up.
Yeah.
But like, what's the cosine of alpha plus beta? What is it? Cosine alpha cosine beta minus sine alpha sine beta? Is that what it is? Who cares, right? So just believe me when I say this is what it is. Okay, great. And then minus sine of x. Yay. And then the next thing I do is I factor the sine of x from the first and third terms. Do you see I have sine of x cosine h, and I have negative sine of x? So I factored sine of x from the first and third terms, giving me that. And then I also have the sine of h cosine of x left over. And then I do what we already saw earlier on another thing we did, when I proved the product rule, where we end up splitting the numerator. So I've got sine x cosine h minus 1 over h as h approaches 0, plus the limit as h approaches 0 of sine of h over cosine of x over h. Okay, I split the numerator. And now here comes the interesting thing. We learned in the first week of school, as a matter of fact, that the limit as h approaches 0 of cosine h minus 1 over h, that limit ends up being a 0. This limit, the limit of cosine h minus 1 over h as h approaches 0, ends up being 0. And we showed that graphically. We just graphed that function, cosine x minus 1 over x. We graphed it on our calculator and saw that it had a removable discontinuity at 0. So this limit is 0, so this whole term just goes bye-bye. And then another thing we did was we graphed sine of x over x and found that that limit was 1. That is, as h approaches 0, sine of h over h gets closer and closer to 1. But this is true only if h is in radians. If h is in degrees, if our angles, if x and h and everything else is in degrees, then this ratio isn't 1. This ratio ends up being pi over 180, right? And we don't want pi over 180. What an ugly number. And so if anyone asks you, why do we always have to use radians in calculus class? Why can't we use degrees? This is the answer. The reason we use radians is because when we apply the limit definition to getting the derivative of the sine, we have to have our sine of h over h as h approaches 0 be 1 and not pi over 180. And that's it. That's the only reason why we always use radians, is just because of this. So I'm hoping you remember from now on, here in calculus class, we're always in radians mode. So this is 1, so I end up with the limit as h approaches 0 of cosine x, which is just cosine x, and there it is, the derivative of the sine of x is cosine of x. Do you believe? Hope so. And if I did the same sort of thing with cosine x, I would end up with negative sine of x. But I'm not going to do it. Alrighty, well that's it. Let's go ahead and do some practice. Here, let me go. Okay. Derivatives of all 6 trig functions. Alrighty. First of all, the derivative with respect to x of the sine of x ends up being the cosine of x. We saw that with the limit definition. The derivative with respect to x of the cosine of x ends up being the negative sine of x. We can see that with the limit definition as well, but I'm not going to do it. Now it's time for us to get the derivative of the tangent of x. Well, I know what the derivative of the cosine is. I know what the derivative of the sine is. How am I going to figure out what the derivative of the tangent is? What? Quotient rule. Oh my God. Zach is correct. Tell me, what should I turn my tangent of x into?
Sine x over cosine.
That's exactly what we're going to do. Derivative with respect to x of sine x over cosine x. Yay. And now let's go ahead and apply the quotient rule. The derivative of the top times the bottom minus the top times the derivative of the bottom. You guys okay with that? Derivative of the top times the bottom minus the top times the derivative of the bottom. All over the bottom squared. What does the numerator magically become?
Oh, 1.
You guys okay with that? That the numerator is cosine squared minus cosine squared plus sine squared, which is 1. So you end up with 1 over cosine squared of x. But if for some reason our book and all other textbooks, they're not satisfied to write it as 1 over cosine squared, they would rather write it secant squared. So that's what we're going to use in this class. Secant squared of x. So the answer to the question, what's the derivative of the tangent of x? It's the secant squared of x. Yes?
So could we leave it as one?
No, I want you to use secant squared. It turns out to make other things a little easier, which is why they chose it. So yeah, just keep it secant squared. It'll be fine. Okay? And then, how about the derivative with respect to x of the cotangent of x? How do you think you're going to find that?
The quotient rule, but with cosine on top.
Quotient rule with the cosine on top, right? You'll get a chance to do that as one of your problems, so I'm not going to show it to you, and I'm not going to have you do it either, because you get to do it as one of your homework problems. But the fact remains, this ends up equaling the negative cosecant squared of x. So the derivative of the cotangent of x ends up being the negative cosecant squared of x. Similarly, the derivative with respect to x of the secant of x. You know, secant of x is 1 over cosine. Could I apply quotient rule to getting the derivative of 1 over the cosine?
You could, but you don't want to.
Well, you're right, I could, and I kind of would want to, if I wanted to spend the time showing you what it ends up being, but I'm not going to go to the trouble. But if on one of your homework problems, they ask for, how, derive the derivative of the secant of x, you would end up doing this. You'd do the derivative of 1 over the cosine of x, and then you would go ahead and apply quotient rule. The derivative of the top times the bottom minus, etc. over, cosine squared of x. Right, but I'm not going to go through the hassle. You'll get a chance to do it yourself. I just want to tell you that the final answer ends up being the derivative of the secant of x is the secant of x times the tangent of x. And then here comes the last one, the derivative with respect to x of the cosecant of x. Just a second. I want you to notice a pattern. Do you notice how the derivative of the sine is the cosine? So the derivative of the cosine is the negative sine? And do you see how the derivative of the tangent is the secant squared? And the derivative of the cotangent is the negative cosecant squared? Right? They're co-functions of each other. So if the derivative of the secant is the secant x tangent x, first of all, do you think the derivative of the cosecant? Well, tell me one thing about it.
It's going to be the co-function of secant.
Good, so like cosecant?
Yeah.
Oh, good. So you're thinking it's going to have a cosecant x. What else is it going to have?
A tangent.
So instead of tangent, what's it going to be?
Cotangent.
Good. And then what's one more thing that's going to have to be true?
A negative.
Good for you guys. Yeah, and that's it. And so all you have to do is remember 3 of them, and then you can remember the other 3 because it'll be the negative cofunctions. That is, if you can remember the derivative of the sine, tangent, and secant, which are cosine, secant squared, and secant tangent, secant of x, tangent of x, then you can remember the other ones where the derivative of the cosine is the negative sine, the derivative of the cotangent is the negative cosecant, and the derivative of the cosecant is the negative cosecant of x cotangent of x. So hey, you ready to do one of these? Did I hear a yes, or was that a no? I forget. Well, hey, let's go ahead and do one. Here, go ahead and get me the derivative with respect to x of the secant of x over the cotangent of x plus 1. Good luck. Please get me that derivative. And then I'm going to have you do another one when you get done with that. Oops. There will be times when I have you simplify, but not good. By the way, if you forget to square the bottom on a problem, but you squared it on other problems that show that you actually did know what the quotient rule was, then I usually don't take points off. You don't forget it, don't make it a habit, but that's the sort of error, again, that I would not take a point off of. I mean, if you've already demonstrated to me you can do it and then you just forgot, I don't know. It's not calculus, you don't know. Hey, how many people got that first one right? Okay, good. And do I have to simplify it? Well, it depends. If you look in the back of the book and the answer in the back of the book looks different from that, then yeah, you should simplify just to make sure your answer matches the back of the book. Especially if the back of the book's answer is like 1, you know, then you go, okay, then there must be some huge canceling that happens here. And then you would go through and go ahead and simplify it. Like, for example, when you multiply secant x tangent of x times cotangent of x, right, the tangent of x cotangent of x multiplied to make 1. So you've just got secant x.
Yeah.
You know? So you see, I mean, there's a little bit of simplifying that's happening here. I mean, secant of x times cosecant of x, well, that doesn't really help you at all. Oh, well, whatever. Have you guys done this one yet?
I'm working on it.
Give it a try. Give that one, and then we'll, then believe it or not, I'm done. Trig functions, baby.
Trigonometry.
Trigonometry. This goes. This goes in here. Yeah, that worked out. Thanks, Abby. Okay, I got it. Yeah. Alrighty, the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Square. How many people got that? Okay, good. Hey, that's all there is to it. So you're going to have to commit these to memory. It's really weird. Unlike the AP Physics test, where, you know, on the AP Physics test, they give you all the equations. They give you all the equations for both the multiple choice and the free response portions of the AP Physics exam. They don't do that with calculus. They give you nothing. And so you are going to have to commit these to memory. But hopefully you'll use them enough that it'll naturally be committed to memory. Are there any questions or issues on this? Then, hey, there it is. That's the homework, and we're done. Good job, guys.